Hello, my name is Jack Yeager. I'm here to submit my physics project 2 on explaining the physics of rainbows. This is aimed at a target audience of around a middle school age, someone who can understand concepts of trigonometry, so sine, cosine, tangent, and angles, just simple angles, and how they can be translated through crossing lines, stuff like that. So here we go, physics of rainbows. So the first thing we need to start off understanding is light. Visible light is a single little section of the electromagnetic spectrum. As you can see on screen, the electromagnetic spectrum ranges from the lowest to the highest of wavelengths. In the low spectrum, you have gamma rays, X-rays, and UV rays, all very harmful to us and have their own uses in many different applications like medicine and growing plants. On the other end of the spectrum, you have infrared and radio waves, which are used for radio communication, and infrared is used for night vision. A lot of cool applications, but none of those we can actually see with our own eyes. We can only see this little band right here called the visible spectrum, from 400 nanometers to 700 nanometers. You'll see me use this in the rest of some parts in the video. The symbol lambda, that is used for wavelength. So if you ever see that, that just means the specific wavelength of light that we're talking about. So we're only going to be talking about the visible spectrum, 400 through 700 nanometers. You got, works your way up the rainbow. So you've got violet, which is like purple, and then you've got your blues, your greens, your yellows, orange, red, and that's how it works. So yeah, the speed of light, which is speed that any form of the electromagnetic spectrum, whether it's a radio wave or a gamma ray, they're all going to be traveling at the same speed, which is this c. It's called the speed of light. It's like a constant. 2.99 times 10 to the 8th meters per second. That's very, very fast. Now, the reason why light can do many weird things and funny things and show us phenomenon like rainbows is because when it travels through different materials like glass or plastic or a mirror or water, the light does different things. And this is due to the fact that it's slower. So when it travels through the water, it's bouncing off of all these different particles and reflecting and doing all funny things. So it ends up in the net distance of the whole chunk of water or plastic that the light is traveling through. It's going to be a lot slower because it's moving in a lot of different directions, as opposed to in a vacuum that just moves straight. This is what we're going to be diving into. So reflection. Let's say this is a mirror. We're going to assume that this object is opaque and most of the light cannot travel through it, like a mirror. So the law of reflection states that on a surface that is opaque and is reflective, any incoming light, so I should say this before, through the rest of this demonstration, we're going to be talking about two different instances of light. We'll say the incident ray of light, or the oncoming, like the ray of light that is before it hits the object, and then the reflected or refracted light. So that's like after it has had the effect of whatever it shined on. So the incident light, or the oncoming beam of light, is going to be like, let's say this right here. This is, we'll just call this dotted line right here. I should say this before. I'm assuming everyone knows what it is, but I shouldn't assume. This is a tangent to the surface. So at any point in the mirror, it's just an imaginary line that's exactly perpendicular to the mirror. So the incoming light here has an angle. We'll call this angle theta. When the light is reflected off of the mirror, it's going to leave at the exact same angle. I forget exactly what it is, so don't mind the angle on the ruler. There we go. So assume this is the same angle. This theta here is going to be the same angle, only on the opposite side of the tangent. So even if it's coming in at like 1 degree, once it bounces off, it's going to leave with 1 degree on the other side, or 89 degrees. But you get the instance. So the angle of incidence is equal to the angle of reflection. It's always going to be the same. Now on some more complicated shapes like a water droplet or a curved mirror, it's still going to behave the same way at the very small scale. So let's say we zoom into the water droplet right here. Because the beam of light that we're dealing with is so small, we're going to assume that the area we're working with, let's say the light bounces off like that, we're going to assume this little tiny distance here, it's going to be flat. Now the tangent is just going to be perpendicular to that flat surface. Same with a curved mirror. If we have light that bounces, say here, then goes somewhere else, at each individual instance, we can assume that because the beam of light, or the particles, the photons, are so small that our surfaces are going to be perfectly flat, and we can assume that there's a tangent right there. One topic that I forgot to mention that we'll just cover right now is that the color of light. So in the real world, not in the digital world, in Photoshop or online in the computer, this logic is not going to apply because colors mix differently in the digital world than in real life. So in real life, white light, which is the light that comes from a light bulb, the sun's really kind of like yellowish, but we'll assume it's white light, a flashlight. White light, we'll call this white light even though it's black. The wavelength is, this is 1 or 2 waves of a certain light. Your wavelength is going to be the distance from peak to peak or trough to trough. Now as you move higher in the wavelength, these waves are going to become longer and longer. And as you move shorter or lower on the spectrum, the waves are going to get shorter and shorter and shorter. So this is like, let's say this is purple, and this would be like red or something. So you've got all these like waves that look like springs kind of, and the shorter they are, the more on the left end of the spectrum they're going to be. So UV rays, stuff like that, and then the longer they are, they're on the right. So our white light is made up of all different kinds, all of the colors in the spectrum. So as we get later in the presentation, we'll show you how those kind of unfold. But yeah, it's just a simple concept. White light has all the colors in it. It's just hidden because they're all in the same little space. So we covered light, we covered reflection. Now we're going to go to refraction. Before we move to refraction, there's one concept you need to understand which will make it a whole lot easier. So, do you remember when I was talking about how light moves at different speeds through different materials? Well, this is where this comes into play. So the index of refraction is it's kind of like a measure. It's a measure of how fast light moves in a certain material. So if you have, and it's never going to be less than 1. It goes from 1, which is a vacuum, all the way up to, the slowest material, or the material with the highest index of refraction. It just means the index of refraction is used in calculations to be able to explain how it's going to move. So all you really need to know to find the index of refraction is the speed of light in a vacuum on top right here. It's in meters per second. And then you divide that by the speed of light through that material. So, unless you're in a science lab, you're not going to know that. But if you go online or on Google, it'll tell you the index of refraction for water or air or, plastic or glass or whatever you're working with. And that's not something we calculate. That's something that's pretty advanced in physics. So usually if you're working with the index of refraction, it'll just tell you what it is. And then you can use it for different things. Alright, refraction. What is refraction? Refraction is the bending of light through a material. So if you notice sometimes when you look at a fish in a fish tank, like if you look at it, like when the two sides of the fish tank are like coming at you, and there's like the 90-degree the corner of a fish tank, and you look at it and you can see fish look really weird in the fish tank sometimes. Sometimes they look bigger or smaller, sometimes they look hidden. That's because of refraction. We'll say this surface 1 right here is air, and we'll say this is water. I believe the index of refraction value for water is 1.3. It's just demonstrational purposes. I don't know if that's actually true, but it doesn't really matter. And air is about 1. It's like 1.00 something, but that's fine. If you have light that's traveling through a vacuum, or air, which we call air vacuum, it's going to move straight. It's not going to bend if nothing happens to it. If you just let it go and do its own thing, it's going to move straight. So let's make a little pathway for light. So let's say a beam of light is just moving through air, right? It's moving at 43 degrees. Comes in, boom, hits the water. Alright, we'll call that our beam of light. Let's say it's blue. So the law of refraction says that if a material is moving, if a beam of light is moving from a material with a lower index of refraction, it is going to move away from the perpendicular. And vice versa. If a light beam is moving into material with a higher index of refraction, it is going to bend towards the perpendicular. If you don't get that, I'll explain it right now. So, a beam of light is moving from air to water. The law of refraction says that if it is moving into a material with a higher index of refraction, it is going to it's going to bend a little bit. Once it crosses that boundary, it's going to bend a little bit towards the perpendicular. So a little bit more towards the perpendicular of the surface. So that means, come on, ruler. That means that if it was moving, if it didn't cross any boundary, it would move like something like this. But because it's moving through a material from a lower to a higher index of refraction, it's going to bend a little bit towards the perpendicular. And that the angle that it bends can be calculated, but that's based on the index of refraction of the material it's moving through. So we're going to say now it's going to bend towards the perpendicular just a little bit. So that's our bending of light. Now, the same is going to happen in reverse also. So let's say we've got 45 degrees. So we've got a red beam of laser moving right there. It's coming in hot. The index of refraction says that if you have a light that's crossing a material boundary with a lower index of refraction, it's going to move away from the perpendicular. So once it crosses that boundary, it's going to move like this. A little bit further away. It's going to like bounce. Just like that. And this is the phenomenon that gives you really weird effects when you see like weird fish to a fish tank, or sometimes objects look hidden underwater. That's the reason why. That's also the reason why in the book Hatchet it was very hard for the main character, I forget his name, to spear the fish in the water, because the fish move. When they move in the water, because of refraction, their position is different from where they actually look in the water because of refraction. So yeah, let me move my camera a little bit. So this is the formula if you want to know exactly where the beam is going to move. So our angles, we'll say, are measured from, call this theta, call this theta 2, call this alpha, call this alpha 2. 1, 2, 1, 2. Cool. So the law of refraction says that if you know the indexes of refraction, we'll call these this one and this one, so in our case it would be air and water, and you know the angle of incidence, or the angle at which the light is coming into the material boundary, that means you know where it's going to exit, basically. So you can use this formula to figure out where the light's going to go, which is very useful. And in my physics class, something we need to know. The critical angle of refraction. This is important. So basically, remember how in our law of refraction we said that light will bend away and towards different materials depending on their indexes of refraction. Well, we run into kind of a conundrum here. And this is where you can get hidden objects, per se. So, at some point, when you have light entering a material with a higher index of refraction, let's say this. No matter what angle the light enters the we'll say water. We'll say this is air. As the light passes the boundary, we'll call this the point of intersection here, where the light moves through the material boundary. It's going to move. If it's moving into a higher index of refraction, it's going to move towards the perpendicular. So no matter what angle the light comes from, let's say it comes from, 80 degrees, or it comes from, this would be like 10 degrees, and this would be like 89 degrees from the perpendicular. It can always move closer to the perpendicular, because the perpendicular is just a figure of imagination. It's not actually there in the water. There's no like line in the water. So let's say that this ray keeps moving forward. It can actually move a little bit closer to the perpendicular because there's nothing actually stopping it. And this incident ray that's coming close to the actual boundary layer itself, it can also be bent a little bit more towards the perpendicular. And there's no issue there. But there becomes an issue when you're moving from a material that's of a higher index of refraction to a material that's of a lower index of refraction. So let's say you've got an angle right here, a red beam that's moving through from water to air. The law of refraction states that a ray or a beam of light coming from a higher to a lower index of refraction is going to move away from the perpendicular. So it's going to keep following a straight path, and then it's going to move away a little bit, like this, by a certain amount. Now, if you keep increasing, we'll call this theta right here, this whole thing. If you keep increasing this theta, the ray of incidence, the ray that it comes into the boundary layer from, at some point, because where the ray exits the boundary, if the ray where it exits the boundary because of the law of refraction bends away from the perpendicular, at some point when you keep increasing the ray of incidence, the ray of refraction, the ray that comes out, at some point it's going to reach 90 degrees, because it has to bend at some point, and if it doesn't bend at all, then there's no problem, because a ray that's coming in at almost 90 degrees can exit at almost 90 degrees, but that's not true because it has to bend a little bit. So at some point, that ray of refraction is going to come out at 90 degrees, which is exactly on the boundary. So it's not, no one above is going to be able to see that light. It's just going to stay right where the boundary is. It's going to be lost, per se. So we call this the critical angle of refraction, because the light is no longer going to be able to escape. So let's say the critical angle's, what is this, 32 degrees. Let's just say it's 32 degrees. So if it's 32 degrees, green light, once it hits this point, will be refracted as a straight line. It won't go out of the surface anymore. We'll call this theta. The actual theta would be more like, what's that, 58 degrees? It's just a figure. So the critical angle of refraction states that any incident ray coming into this material boundary that has a higher angle than the critical angle will just reflect off of the surface. It won't actually exit the water into the air, it'll just bounce off. And this is a phenomenon known as total internal refraction. So, and this angle is set by the difference in indexes of refraction. So if a ray of light comes in at an incident angle higher than the critical angle of refraction, it will be totally internally reflected inside the material, and it will never escape. You can calculate this using this formula. If you for indexes of refraction that are higher and that are going from high to low, you just put this in this formula and you'd be able to calculate at what angle is the steepest angle that you can have light exit the material. And so this is why you can, fish have different position than what they look like in the water. why the main character in Hatchet was not able to spear the fish in the book, and why sometimes you can have hidden objects. A common use of this, which you may not think of, is fiber optic cables. I don't know if you've ever heard of this. I used to have a fiber optic cable in my Xbox headset. They are used for they're a very new source of internet transfer cable. They're used, in the stock market. They're very advanced technology used all over the world, and it uses this property of total internal refraction because the index of refraction for the fiber optic cable itself is very, very high. So it's very, very high. I don't know what it is, but the highest, no, it's not the highest, but it's high enough so that most of the light that is sent out by this, we'll call this a bulb, whatever light source from the computer that it wants to send, a lot of it always just bounces inside, and it keeps bouncing because the critical angle of refraction is just so high. So all the light that tries to escape just keeps bouncing and bouncing and bouncing. So all the light just keeps bouncing and bouncing and bouncing and moves throughout the cable. So wherever you bend that cable, you can have light that moves like that. And the last topic that we need to understand is the dispersion of light. I'll move it. Dispersion of light. And this is what we need. Oh, this is a little thing I made. This is what we need to understand rainbows. So what the dispersion of light says is that when light is refracted from one surface to another, different colored lights bend more than others. So, and you can see my chart here. So if, let's say, we're dealing with a ray of white light, this is where you get the classical image of the Pink Floyd album cover, or like a prism where light enters a prism and gets dispersed, basically. So red light is going to bend, it's going to be affected by dispersion the least, and as we move lower in wavelength, well, let me use my lambda here, wavelength, as we move lower in wavelength, the more the light is going to be susceptible to dispersion. So what do I mean by this? So let's say we've got white light represented by my black marker, comes in at 45 degrees. That means that when it crosses that boundary of refraction, so let's say it bends by, 10 degrees or so, your red light is going to be the least bent of all the colors. And then you've got orange, and so let's combine this orange and yellow. It's going to bend a little bit more, just a little bit. Then we have yellow, we have green, it's going to bend a little bit more. And blue, which causes it bends like this. And you get the idea. So this is where the concept of a rainbow comes from. Because if you have white light that's being refracted from a material, it gets dispersed into from the material. Now, different materials and different indexes of refraction can affect the dispersion differently. Water is a good use for this. So rainbows are made from water droplets in the air, and prisms are also very good at dispersing light. And this is where you get your rainbow effect from. I'm going to now explain very quickly how I'm going to create a rainbow and how you are able to see rainbows, out in the wild. So let's explain the regular rainbows first. So 2 things are needed to create a rainbow. You need sunlight that has all the wavelengths of light, because you can't create a rainbow with just red light. It would be a rainbow. Or red rainbow. And you need rainbow. Let's create our water droplet, because we need a water droplet. Let's create sunlight. Boom, boom, boom. Shines in the sun. And we'll create our person. So what happens is when light hits the water droplet, in reality, there's a seemingly infinite number of rays of light that's hitting this water droplet. And they're going to come into the water droplet, and they're going to bounce in all different directions and reflect and refract basically everywhere. But from where we're standing, the only light that we're going to be able to see is light that's coming directly from the raindrop to our eyes. That's the only way we can see it. So the only light that we care about is the light that's going directly to our eyes. Let me erase all these. Okay. So the way that light works in a rainbow is very weird. So let's look zoom in on our circle. Assume this is a circle. This is a really bad circle, but that's fine. So let's say light moves in right there. All right. So the first thing we need to do is we need to make our tangent. So to make a tangent for a circle, you just put a dot, and then you draw a line. It's good enough. Now remember when I said for tangents on curved surfaces, you can assume at that instance where the light hits the water, because the light is so small that at a very, very small scale, the water droplet surface looks flat, even though it's curved. So it'll still behave the same way, even though it's on a curved surface. So, what happens to the light? So, the law of refraction states that the ray of light is moving from a material from a lower to a higher index of refraction is going to move towards the perpendicular. So the light coming in from our tangent here, we'll say, sorry about my hand, we'll say this is, 6 degrees. Doesn't really matter. It's going to be bent from, so this is a perpendicular, this is a ray of light. It's going to be bent towards the perpendicular a little bit. Now what also happens is the light gets dispersed a little bit too. So, for those of you who didn't know, when you see a rainbow, on the top there's red, and then orange, and then yellow, and then green, and then blue, and then purple. Where's my purple? Purple's at the bottom. That's what a rainbow looks like. It's never really the other way around. Red's usually on the top. I'll show you why. So, as I get my ruler out, we'll say light comes in at this angle, and it's going to move a little bit closer to the perpendicular. We'll say it moves here. Is there a red light? At the other end of the spectrum, you have purple, which I'm going to demonstrate as blue. I think I have a purple color. There we go, I do. Okay. So we have, well, it'd technically be violet, but we're just going to say it's purple. It's going to be diffused just a little bit, like that. And you have all the colors in between, but I just don't want to draw the colors. So now they're getting refracted a little bit, they're being bent a little bit, and they're also getting dispersed into all their colors. So we're going to follow these. Boom, there's a purple light. And there's our red light. Now, because they have now moved closer to the closer to the perpendicular, now these rays of light they do not have enough angle because of the critical angle of refraction to exit the water. This is just like this is why the light, or why the sun has to be on the other side from the water or the rain as the view of the rainbow, because once it gets refracted once, it gets internally reflected in the water, and it comes back out. So let's say our tangent is from the center of the circle. I know this is a very poor circle to here, and this one goes there. Come on. There we go. Nope. There we go. Okay. So our two little tangents. We're going to draw our red as best we can. Gets that. So we're looking at, if you can see my cursor, this is our red line that is being reflected, internally reflected, and this black line is the tangent for the red line. So the red line is now going to be internally reflected all the way up here, and the purple is going to be like this. There we go. So as you can see, inside the water droplet, the colors actually flip. So now the red light on the back on the incident side, well, it's already in the water droplet. The red light is on top and the purple light is on the bottom. When they get reflected, they cross. So the red light's on the bottom and the purple light's on the top. And once they get reflected, then they have enough juice, per se, to leave the droplet. Or, not juice. They have enough at an angle of incidence that is lower than the critical angle of refraction. So they're allowed to exit the water droplet. So let's just say, well, we got to draw our tangent now. And if I had the measurement of my water droplet, and I could be able to draw a perfect circle and perfect tangents, then this would all be much better, but it's not. So a water droplet is going to move away from the perpendicular. This is all for demonstrational purposes also. This is not, my model is not scientifically accurate at all. Because a rainbow you're not going to be seeing a rainbow from the ground, you're going to be seeing it from the air. So we're actually, because of my drawing, the light should actually be coming out of the droplet, down like this, even though on my diagram it said it was going to be going the other way. I drew the diagram poorly, so it's not demonstrating this. But we're going to say, for demonstrational purposes, that this is what happens to the light. So, now you've got your viewer. So, what we're going to do here is we're going to demonstrate how you can see it. So, like I said before, we only care about the light that's hitting our eyes. So when you see a rainbow, you have sunlight that's reflecting onto hundreds of millions of water droplets that are in the air. As the water droplets each get reflected off of many different angles of light, you have light at this angle, or a special angle. It all depends on where the water is and where the sunlight is and where you are. But this concept of internally refracted, reflected, and then refracted light happens in all these raindrops, and all the angles change, but the principle is still the same. So you have your person, your viewer. Let's say they're here, right? They're going to be able to see if that red line continues and goes straight to where a person is at this location, right, of this water droplet right here. They're going to see red light because the red light's going to continue to hit their eyes. But let's say that we're going to back this up. My computer can't handle me moving the whole water droplet. So imagine I'm moving the whole water droplet. I'm not moving the person. If the water droplet was a bit lower, so like this, let's say it's a lower water droplet. Now the red light won't be seen at all from the person because the person had to be way down here in the ground or something. Now the water droplet is lower, they're going to be able to see the purple light, or the lower end of the electromagnetic spectrum, but they're going to see those lower colors at a lower height because as they get refracted, reflected, and refracted, through getting dispersed, they're going to cross, the rays are going to cross, and so when this phenomenon of rainbow happens at a lower height, they're going to see a lower end of the spectrum. So you have your person, and they have a weird head. That's okay. We have hundreds of millions of water droplets. Hundreds of millions of water droplets. Maybe even billions. All scattered in the air. As sunlight hits them, your red lights are going to be reflected and refracted, and are going to hit your eyes at a higher height in the cloud of water droplets. And then the yellows will be seen at a lower height. And then you get your blues. I'll pretend this is not the same color as water. And then your greens. Red, orange, yellow, blue, green. I think right. Red, orange, yellow. Oh, green, blue. My bad. I messed up the rainbow. Green is before here. I should have known that. And purple or violet. And that's how you get your rainbow effect. That's how you can have rainbows appear in the sky out of nowhere. It's actually sunlight that's being refracted, reflected, and refracted off of hundreds of millions of water droplets. And that's how you observe rainbows. In my experiment, I could not recreate the rainbow through hundreds of millions of water droplets. It was kind of a failure. So my plan two was to have a prism. It's actually a 90-degree prism, like this. And we have our beam of light. Now, what's hard about this experiment is that because the sun, when making rainbows, because the sun is so far away, all of the rays of light that are coming at all the water droplets are pretty much perpendicular because the Earth is so far from the sun. But if you take the sun, because the sun's at one location, shining in all directions, in reality, they're not perpendicular. They have different angles, all the seemingly infinite numbers of rays of light coming from the sun. But because the sun is so far away from the Earth, when the light rays get to the Earth, they're pretty much perpendicular. And for, science like rainbows and physics, we can assume that they're all perpendicular. Now, my flashlight that I'm using to create my rainbow is so thin, or not thin, the angle at which light leaves my flashlight is so wide. When you shine that wide of an angle at a very close object, you're not going to get perpendicular lines of light. And when you don't get perpendicular lines of light, you're having light that is going to be scattered. It's going to be pretty much distributed evenly across the whole prism. So there will be a dispersion of light in the prism, but because every single ray of light that's hitting the prism is being dispersed in some way, it's going to dilute all the rainbows that are being viewed, and it's just going to be viewed as white light again. Because once they get separated, they're going to get mixed with all the other colors that are also being separated, and it's going to end up being white light. So the trick is you need to make a beam of light, it's like a laser basically of light, so that we can show how one light gets dispersed into the colors instead of hundreds of them. So in my experiment that I did, I took a paper towel roll, and I took an aluminum sheet with a very, very thin line through it. And I put the two and two together, like so. And I wrapped the aluminum sheet around the paper towel roll, and took my flashlight and put it inside the paper towel roll, so that, there we go, so that the rays of light coming from the flashlight hopefully get absorbed by the cardboard or reflected off of the tinfoil, and it all gets absorbed in the cardboard. But hopefully, the only light that is going to be able to be passed in my dark room will be the light that's coming directly from the flashlight and is directly opened by the slit. So hopefully, light that passes through will only end up being a beam of light onto a wall. And so then I will be able to shine it on my prism, just like this, have it reflected and refracted into a beautiful rainbow. But we'll see then. Thank you for sitting around and hearing me talk about rainbows. Next, you should see me do my little experiment. Thank you again. All right, this is the apparatus. So we've got flashlight that's in the toilet paper roll with the slit. The reason why the flashlight is angled on the side is because the beam would become much wider and it would become more of a chunk of light. Yeah, just like that. But as you move it to the side, a lot more of the light gets internally absorbed by the cardboard, and it becomes more focused into a beam. So if you move the beam over to the prism, just like that, you can see how all the light beams get reflected and refracted off into different angles. And as we move the prism around, you can see that the angle at which the light moves differently. And you can see right there that we've got one little rainbow. So you can see how the blue and ultraviolet lights are to the right, and the red. You can see how the red lights get reflected or refracted less than the blue lights, and the blue lights move more than the red lights because the blue ultraviolet lights have a higher frequency. I mean wavelength. Sorry. So we can get a better video of this. See if we can get a better rainbow. I don't think we can. You can see here there's another rainbow. You see the blue light and the red light. The blue light's getting reflected more on the right. On the left side, you can see that the blue light is now on the left because it's getting bent and refracted more than the red light.